When we're talking circles, one thing that comes up quite often are inscribed angles and intercepted arcs. Now, in order to understand this concept, we're going to have to remember a few things. First off, don't forget what are called central angles. When we're talking about a circle, a central angle is an angle whose center is at the center of the circle. So here I have this lovely angle and I have the vertex at the center, so that makes this a central angle. And in a circle, the central angle is always equal to its arc measure, which we can see right here. Now remember, arc measure is not talking about the length of the arc. All it's saying is how many degrees out of the 360 did you go. So in this case, if let's say my arc measure was, well, it looks like it's a little over 90, so let's go 96 degrees. The central angle will also be 96 degrees because they match up. When we're dealing with inscribed angles, we have a bit of a change. The inscribed angle is one whose vertex is not at the center of the circle here, but it moved to a point on the circle. And now you can see here that the angle itself then will have sides that are chords on this circle. So let's go ahead and mark that in. This is our inscribed angle. And it also is going to form what we called an intercepted arc. Now, an intercepted arc is just one that's inside that inscribed angle. In other words, you can kind of think about these as like arms extending out from that inscribed angle. And the piece of the circle that it catches is that intercepted arc. So here is our intercepted arc. Now, of course, these are going to look different in different circles and with different drawings. We can have ones that are very like long and narrow, like that. This is still an inscribed angle down over here since its vertex is on the circle, and its intercepted arc is small and over to the side here. We can have ones that take up almost the entire circle when it comes to the intercepted arc. So ones like this, you can see that my inscribed angle is right here. My intercepted arc is taking over the vast majority of the circle. That's completely fine. And we even have a special case here that's going to actually establish our algebra principle. Let's say you drew in a diameter on a circle, and you made an intercepted arc where the two chords that make up the sides touch at the ends of the diameter. Now look at this intercepted arc that I just drew in. In this case, it looks like it's about 90. And if I look at its intercepted arc, since that intercepted arc meets at the diameter, I know that that has to be 180 degrees because it's half of a full circle. So that means that it kind of looks like what's happening is whatever angle I have here is going to be doubled to get to the measure of this arc. And that is exactly what's happening. We end up with this formula. The intercepted arc, so I'm just going to write measure of the arc, will be equal to 2 times that intercepted angle. So that means if I'm looking at this figure, if this angle was 45 degrees, this arc would be 90 degrees. In this angle, if the angle was 10 degrees, the arc would be 20 degrees. And with this one, well, we'd have to have a pretty big one. That's getting close to 180. If this angle was, let's say, 135, I would just double it. And I could say then that this would be 270 degrees for the angle. Again, keep in mind that we are not talking here about length, we are talking about measure. So everything we do will get degrees when we're working with inscribed angles and intercepted arcs. Of course, not all of these will be this straightforward. Once you get used to just doubling or having these measures, you're going to get slightly more complicated pictures and slightly more complicated formulas. So let's look at a few of those. So we'll start with this one, which starts out with just practicing the core concept. In this one, let's say I wanted to find the measure of the arc DC. Well, the measure of the arc DC is talking about this arc right here. And notice that I can see that it's being cut off by 2 lines, and I can kind of extend those lines. Now this helps me trace it back to the angle that matches up with it. This is my inscribed angle. And since the inscribed angle will always be half the size of the arc, I can double this and I end up with a degree of 90. If I look over the top here and let's say I wanted to find the measure of the angle ADB, well, I can kind of start at this angle and go, this is the angle that I want to find. If I extend those lines outwards, I notice that it intercepts this arc up here, which is 76 degrees. I know that this one will be half as big as the arc that it intercepts, so I can take 76 and divide by 2, and that will give me 38 degrees. I can also do more complicated formulas. Looking at this picture here, it can get overwhelming and confusing because I've got like a couple triangles, I've got this circle, I've got the center, and then, oh great, some algebra thrown in. But it's actually not nearly as bad as it looks. When you have an overwhelming picture, break it down to its pieces. Notice that it's telling you that this angle is 3x plus 25. Well, if it's talking about this specific angle, let's look at this angle independent of the rest of the figure. I like to darken it with another color or with my pencil, just so I can kind of focus on that and ignore the other shapes, only looking at the color that I'm drawing with. Well, I know that anytime I have this extended angle, the arc that it intercepts will be double. So I'm just going to shade that in so I know to pay attention to it with this angle. And when I do that, notice that the 2 pieces of information I have actually are fully connected. I don't even need these other 2 lines. I can ignore them completely. This measure is half as big as this one. So if I do 2 times the angle, 3x plus 25, I should get my arc of 5x plus 60. This is then a problem I can solve using distribution. So I'm going to start by distributing that 2 to get 6x plus, well, 2 times 25 is 50. And that equals 5x plus 60. And here to get x by itself, I can subtract 5x from both sides. That cancels out that 5x to leave me with just x on the left. And I can then subtract 50 from both sides to move that away from the x. And 60 minus 50 is 10. So I find here that x equals 10. Of course, the question might be asking for x. It might ask for what the measure of the arc is, in which case you can plug that x in, or it might ask for what measure the angle is, and again, you can plug that in. So we can quick find that. 3 times our x value of 10 will give us 30. 30 plus 25 gives us 55, so we can find that this angle is actually 55 degrees. Now, without even further solving, I can say that this should be 110 because it should be twice as big as this one, but you can always double check. 5 times 10 is, well, that's 50, plus 6 does give us 110, so it looks like we did that correctly since both of those answers make sense. Now, of course, sometimes we're going to have issues where the arc is intercepted in more than one place. Let's just start with this B. We want the measure of the arc WX, so I'm going to color that one in. And as soon as I do, I notice that there's a bit of a problem. This one doesn't have an intercepted angle to work with, and it's like this piece of an arc. So what I'm going to do is I'm actually going to look for an angle that does have this arc in it to see if I can find a pattern. And if I'm kind of like looking around, I can see that this chord is on there, so I'm going to extend that chord a little bit. And that one does have an angle associated with it. It's way over here, so I'm going to extend that out. And that tells me that this overall thing is an intercepted arc containing our arc. Now this is helpful because if I look at this, I know the pattern. This this inscribed angle is 55 degrees. I can double that to get 110 degrees out here. Since this is 110, I can subtract 60 to find what this little piece would be, giving me an answer of 50 degrees for WX. That leaves us with one final problem. And while there are multiple ways to solve it, I'm going to walk you through my favorite way. So once more, I have a bunch of things in a circle, and it can be easy to get lost. But if I know that this is talking about an angle which is inscribed because its vertex is on the circle, I can extend it out and highlight my arc. Unfortunately, I don't actually have more information than that, so I'm just going to do the same thing with the other piece of information given to me and see if I can spot a pattern. So I see that I also have this angle, so I'm going to extend this blue angle out, and I'm going to shade in its arc to see if there's a pattern, and sure enough there is. Looking at this, I now see that I have information that relates to the entirety of the circle. And we know that circles add up to 360 degrees. So if I know the measure of this arc, and I know the measure of the blue arc, I'm going to be able to create a formula adding them up to 360. Well, I know that the blue arc is going to be double 2 times 4x plus 9. And I know that the pink arc is going to be double this angle that intercepts it, or 3x plus 3. I can add those together, and I'll get 360. So here, use your distribution. Be very careful when you get this many variables and numbers. It's easy to make a little mistake and mess up your whole problem, which is especially frustrating when you do everything else right. So take your time with these. And we can combine 6x plus 8x is going to give us 14x. 6 plus 18, well, we are going to end up with 24. And now we're back to normal solving. So go ahead and take 360, subtract 24 from both sides, and you get 336 is equal to 14x. Dividing both sides by 14, I end up with a final answer of 24. So those are some ways that you guys can use inscribed angles and intercepted arc to solve for missing measures and also to find x's in various problems. Keep in mind that the pictures will often look very, very different, but if you break it down to the angles and their corresponding arcs, and maybe draw in a few extra things on the circles, you should be able to spot a pattern.